Hello, my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on nitrogen and sulfur. And this is topic 12 of the CIE or Cambridge International specification. So obviously in this topic we are going to be looking at the kind of dual topics, I suppose, a dual content of nitrogen and sulfur compounds and pollution and that side of it. So if you are studying the CIE specification, this video is perfect for you. There is a full range of topics available for the CIE specification on Allery Chemistry YouTube channel. All I ask is you hit the subscribe button just to show your support. That'll be fantastic. Also, the slides that you see here are available to purchase, and they're great to supplement your revision as well. So if you just click on the link in the description box below, and you can get a hold of them there. They're great for, say, kind of on the go, put it on your phone, your laptop, your tablet, etc. So it's just a different way of revising. So the notes here, but you've also got the narrative to go with it as well with this video. Okay, so let's make a start and let's have a look at, probably a best place to start is the chemistry of nitrogen. I suppose, why not? Nitrogen naturally exists as a diatomic molecule. So diatomic obviously means that it's di meaning two and atomic means atom, so it's two atoms joined together. So nitrogen, along with, say, the halogens, for example, as well as oxygen, other chemicals, hydrogen, for example, are diatomics. So nitrogen is obviously in group 5, and it has the electron configuration of 1s2, 2s2, 2p3. So it forms obviously a covalent bond, and it's a triple bond between nitrogens. There's quite a strong bond between it, and obviously, like I say, it's a diatomic. Now that triple bond gives it this kind of unreactive property, so it doesn't really react with a lot of things. It's obviously a gas at room temperature and pressure, because obviously the majority of the air that we breathe in now is nitrogen. So yeah, thankfully it's an unreactive gas. With it being a triple bond, obviously there's 3 pairs of electrons are shared in that triple bond as well. So this is like a dot cross diagram. Okay, so let's have a look at some common nitrogen molecules. So nitrogen reacts with hydrogen to form ammonia and ammonium ions as well, as you're going to kind of see in a moment. So ammonia, excuse me, as you've seen before, has the formula NH3 and is made through the reaction of nitrogen and hydrogen. And you've obviously seen the Haber process in the past as well in previous topics. So ammonia shares 3 of its valence electrons with hydrogen, and a lone pair of electrons remains. So you can see there's ammonia there, okay, which is NH3, quite a common molecule, very important molecule actually, as you'll see, because it's even got a whole topic dedicated to it. And because of the lone pair of electrons, ammonia can actually form hydrogen bonds, as you've probably seen in topic 2, and it can react with water. It can form hydrogen bonds with water, so it's actually quite soluble in water, which is useful because it means we can do a lot of reactions with it. So in addition, like I say, ammonia can also form dative covalent bonds as well, also known as coordinate bonds. And this is because it has this lone pair of electrons. There we are there. So it's got the lone pair of electrons that allows it to react. So let's have a look at this here. So your dative of coordinates, remember, is where you've got one atom, in this case the nitrogen, donates a pair of electrons to another atom or ion to form a bond. So let's have a look on here. There we are. Okay, so the hydrogen or the proton basically shares the 2 electrons that were lone pair on the nitrogen, and this is your coordinate bond. It's not the same as a standard covalent bond where you've got a dot cross there, as you can see. This is weaker than a standard covalent bond, which actually plays into its favour, because actually you'll see later on it means that it's quite reactive. It can react with certain things as well. So the lone pair as well on ammonia it means it acts as a base. So remember, bases or Bronsted-Lowry bases are proton acceptors, so they will accept this proton. So effectively, ammonia is acting as a base, and it's forming this ammonium ion, which looks like this, and the ammonium ion is NH4 plus with that plus charge. So it's got this additional proton attached to it, and it's represented, the dative covalent bond or the coordinate bond is represented by the red arrow that you can see on there. Okay, so let's have a look at some nitrogen molecules and some reactions, I suppose, to them. So ammonia, right, that's a bit weird. Ammonia can be displaced from its own salts. Okay, so in other words, we can make ammonia from a salt of an ammonia through a specific type of reaction. And this actually boils down to that proton that we'd seen in the previous slide, that additional proton with that weaker coordinate bond. And it's that weaker bond that means it's more susceptible for reaction with other substances, and it's lost quite readily, and that means we can actually liberate ammonia from ammonium salts. So here we're going to use ammonium sulfate, which is the salt, and it reacts with the base of calcium hydroxide in this case, which is CaOH2, which you will have seen in the group 2 topic, and we can liberate ammonia from this. So you can see on this reaction here, you have ammonium sulfate, that's your salt there, reacting with the base, calcium hydroxide. That forms calcium sulfate plus ammonia, there's your ammonia there, and water is produced. So we've liberated ammonia from its salt, an ammonium salt here. Okay, and we've done that by reacting it with calcium hydroxide. Now, this reaction as well is also a test for ammonia. I'm going to have a look at this reaction here. Okay, so we can use, or we can test for these ammonium compounds by adding sodium hydroxide, so gently heat it, an ammonium compound is present, then we will get ammonia gas that's being produced. So this reaction here is a test for ammonia. So we can obviously add calcium hydroxide to an ammonium compound, like an ammonium salt, and we'll produce ammonia. And this is the test that we can do to try and detect ammonia. So here we'll just use a different chemical here this time. Instead of using calcium hydroxide, we can use sodium hydroxide, gently heat it, and if ammonium compound is present, we will get ammonia gas. And we test for ammonia gas by using damp red litmus, which is this here, and ammonia will dissolve in the water and it'll turn this litmus paper blue if we've got ammonia present coming out of this test tube. And we see there's the ionic reaction there. Okay, so this is a good way of testing for ammonia. We basically use an ammonium compound, so ammonium salts, and adding the base in there will liberate the ammonia. Okay, so nice and straightforward. You might have done that in the lab as well. So, okay, so let's have a look at some of the uses of ammonia and its compounds. Obviously, we need to know the uses of ammonia, what you actually do with it. And again, we've touched on this in the previous topic, and you'll find with CIE there's a lot of overlap with the topics anyway. But we need to know about the uses of it and the manufacture of nitric acid as well. So we're going to start with ammonia first. So ammonia is incredibly vital. It's used in the agricultural sector extensively, and it's used to help as a fertilizer. Now, without ammonia, we wouldn't be able to produce the volume of food that we do produce nowadays, and that allows us, obviously, countries to feed their citizens and allows us to have the food that we have, etc. So it is an incredibly vital reaction. And it's made using the Haber process, which you will have seen in topics 7 and 8. So obviously that's a very important process. Obviously, common fertilizers are things like ammonium nitrate, ammonium phosphate, urea. So these are all substances which have been derived or will use ammonia as part of that process. So a really vital chemical to use. Okay, the other one is the manufacture of nitric acid. Now, nitric acid is a very important bulk chemical. It's used to make other products such as maybe pharmaceuticals and paints and coverings, etc. So it's a really important base chemical. And nitric acid is actually initially made by reacting ammonia which could be made from the Haber process, for example, with oxygen to form nitrogen monoxide. So that's the NO bit. And then we can take the NO and react it with more oxygen, so basically just heating it up, to form nitrogen dioxide, which is NO2. And then we can go a little bit further and we can say, right, well, the NO2 actually exists in equilibrium with N2O4, which is this chemical here. And then we can then take the N2O4 and dissolve that in water, and that forms our nitric acid, which is HNO3. So you need to be aware of these reactions here and how you obviously make ammonia through the Haber process, but also the uses of nitric acid as well, which is obviously quite an important chemical. Both are obviously very important, very vital. Okay, so let's look at the environmental effect of nitrates, because obviously this forms quite a big part of actually this topic. The environment, obviously, nitrates do have their benefits in terms of food production and anything to do with, say, base chemicals to make pharmaceuticals. But nitrates can be produced, for example, through the combustion of fuels, which can lead to issues for the environment. So it does have its downsides as well. So, like I say, nitrates are used commonly or found commonly in fertilizers. However, if they're used incorrectly, they can lead obviously to environmental problems. So if we use ammonia-based fertilizers like ammonium nitrate, for example, they're useful to help crops grow in a field. They obviously help to kind of fertilize the soil and make sure that you get healthy crops out of it and get a good yield as well. Obviously, that is really important. However, if we use too much of it on the field, and sometimes this happens, then we get some of it leaching into rivers and lakes. And the big problem with this is that nitrates in the water can affect babies under 6 months. So we've got to be really careful about treating water and where that's actually provided. So it reduces the ability to carry the right amount of oxygen in the blood, and sometimes we call this condition blue baby syndrome. So we've got to be really careful, obviously, with that. With obviously water and what we give to babies, and make sure the water is actually kind of filtered properly. But the other one as well, and this, again, people who maybe study geography or biology will probably be more aware of this, but obviously if you've got excess fertilizer, it promotes the growth of aquatic plant matter, so you get like algae that's growing, and this leads to higher than normal vegetation in the rivers. Now, obviously, they'll die eventually and they'll decompose. And the impact of that is they will reduce the oxygen level in the water, because obviously decomposition will use some of that oxygen up. And this means you've got aquatic animals like fish will struggle to survive because there's less oxygen. And this kind of process is called eutrophication. A really important process because it can destroy the biodiversity within streams and rivers, which is vital for aquatic life to live. So yeah, we've got to be careful on that side as well. So it does have its downsides. So farmers have got to use these responsibly, and they've got to make sure that they're not putting more on than they need. And a lot of farmers are trying to reduce the reliance, I suppose, on some of these fertilizers, and maybe use organic, natural alternatives. But simply it might not be feasible to do that, and so that's why we do still need developments, I suppose, fertilizers like this, because it just isn't practical for some farmers in the way they work. So yeah, so it does have its downsides. Now, obviously, nitrates also exist within vehicles. So these are obviously combustion-based cars. Obviously, as time goes on, we're probably going to be moving away from this. And obviously, within the UK, there is obviously legislation in place to try and move people completely off fossil fuel, so petrol and diesel cars, and use electric cars instead. So this is obviously to do with combustion engines. So nitrates, obviously, such as nitrogen monoxide, NO, are formed in cars, and they're made by simply reacting nitrogen and oxygen, which are both naturally found in the air. But when they get pushed through an engine, which is really hot and then compressed, it creates a reaction, which basically puts them together, so combines them together, and this obviously produces NO, which is nitrogen monoxide. So these are two compounds which are, or two elements, nitrogen and oxygen, which are naturally found in the air, but through the process of combustion, they combine to form NO. Now, NO in the atmosphere is not good. We don't want that in the atmosphere. It causes problems, you'll see in a moment. So cars are fitted with catalytic converters, which help to reduce the levels of carbon monoxide in the atmosphere. So that's obviously produced from the incomplete combustion of fuels, and it reacts that with nitrogen monoxide. So we're trying to remove two harmful chemicals from entering into the atmosphere. And you might have seen this before, but effectively we use alloys. So alloys of platinum and rhodium and palladium. So these are catalysts effectively. So there's a catalytic converter in the car, and it converts carbon monoxide and nitrogen monoxide into carbon dioxide and water. And obviously the catalytic converter is found underneath the car. So if you ever have a look underneath, there's a box that sits underneath, normally about halfway along the car, I think. And this is basically the catalytic converter that sits in the car. So this is obviously quite an important reaction. But again, it's NO, we don't want that into the atmosphere. The issue is we now produce carbon dioxide, which we also know isn't very good, because it can cause, it does, it's a greenhouse gas, and obviously causes or contributes towards global warming as well. Okay, so let's have a look at some of the environmental effects then of, say, nitrates, so nitrate-based compounds, and what do they actually do in the environment? Why are they actually so bad? So nitrogen dioxide, NO2, acts as a catalyst in the formation of sulfuric acid, which is H₂SO4, and actually that is the cause of acid rain. And this is why I want to try and reduce some of these chemicals from getting into the atmosphere. It's a bit of a long process, but it all starts with nitrogen monoxide, effectively. So remember, that was produced from burning fuels in a car. So that nitrogen monoxide reacts with the oxygen to produce nitrogen dioxide. Okay, so that's the first process. So that obviously oxygen is naturally found in the atmosphere anyway. As you can see here, there's your oxygen there. Nitrogen monoxide from fuels, that can produce NO2. And it's this NO2 that is then used as a catalyst in the atmosphere. So the main component of acid rain is obviously sulfuric acid, that's H₂SO4. So NO2 basically starts by catalyzing sulfur dioxide that may be in the atmosphere through, say, burning of fuels. Again, you might get some sulfur dioxide produced, and it produces SO3 and NO again. Okay, so NO, remember, can go back round, form oxygen and NO2, so it can it forms like a cycle, I suppose. And then this SO3, we've got the NO2 is reformed, so obviously that's obviously remade back again, as you can see there. And then what happens is the SO3 produced from step 1, that reacts with water in the atmosphere that forms this sulfuric acid. So the issue here is that actually once the NO is in the atmosphere, it kind of catalyzes itself. Unless we start to reduce the amounts of this going into the atmosphere, then it poses a problem longer term. And this is one of the reasons why a lot of countries are looking to remove the requirement of producing these harmful toxins that go into the atmosphere, such as obviously from cars, and use electric cars and generate the electricity through renewable sources such as wind and solar, and even nuclear to an extent, although it's not technically probably not classed as renewable, but it's it doesn't produce, it only produces water rather than, obviously it has the nuclear waste side of it, which is a big issue. But it's another area in which we can use that to try and reduce these pollutants from going into the atmosphere at least. Okay, so one of the other areas we need to look at is photochemical smog. Now, this is obviously produced through, when you burn a fossil fuel, not all of the fuel will burn, and you get some unburnt hydrocarbons that come straight out the back of a car exhaust. And the oxides of nitrogen that we've talked about before through combustion of fuels, these can lead to photochemical smog at lower levels. So we've got some interesting pictures here to show you in a moment. Effectively, ozone occurs in the lowest level of the atmosphere, so that's where it is. So that's in what we call the troposphere. Okay, so this exists as sunlight, hydrocarbons, and nitrogen dioxide mix to form ozone, and that's basically how it's created. So a great deal of the hydrocarbons and nitrogen dioxide, they actually come from cars and factories, and this is where this kind of creates a problem when it mixes with the ozone that's at lower levels. So this is, you can see kind of an example of this photochemical smog. But when you've got solid carbon particulates and ozone mixing in the atmosphere, then we create this photochemical smog. And this was actually taken in Shanghai, in China. So, and obviously you can see, you might see quite a bit of this in any major city, to be honest. It's quite it's quite a dim picture, isn't it? When you see all the pollution, obviously, in the atmosphere. So photochemical smog, it harms the respiratory system in animals. It's not good for you at all. It damages plants. Obviously, they can't respire properly. And ozone is actually toxic to humans. We don't want ozone at lower levels of the atmosphere. It needs to be higher up. And ozone is there to help protect against harmful UV coming into the atmosphere. So this photochemical smog, it can be released. It can be stopped by the reduction of pollution entering the atmosphere. So it's an easy solution, but it's a case of you've got to generate energy, you've got to make things. The key thing is moving away from this and using different alternative sources, should we say. So another one, obviously acid rain, and we mentioned about this before. So burning fossil fuels do release sulfur dioxide. I know we kind of talked about this just a little bit before, and obviously releases oxides of nitrogen, and it's them substances which contribute to acid rain. So we can see, obviously, acid rain causes extensive damage to plants, mainly plants, and it can kill fish as well, obviously in rivers, because the waters become acidic and the plant biology changes, and we get erosive effects on buildings. If you look around, wherever you live, the rainwater is generally acidic, slightly acidic anyway, but obviously in areas where there's a big acid rain problem, then you've got issues with buildings starting to erode away. So if you look at some of the older buildings, particularly buildings with detail on or design features that over the years has been worn away because the building might be made of limestone or sandstone or anything like that, then you're going to get the effects of this. You can probably see it more often. Normally gravestones, you can see that quite often on gravestones. So some fossil fuels obviously contain sulfur-based impurities. It just can't be helped. When you burn a fuel, there's sulfur in there. And obviously when we burn that fuel anyway to generate energy, then the sulfur that's trapped within the fuel naturally reacts with the oxygen to form this sulfur dioxide. And then obviously that sulfur dioxide is an acidic gas. It reacts with the water in the atmosphere. That produces your acid rain. And then nitrogen oxides also do the same as well. So you can get nitrous oxide, you can get nitric acid. But the main form of acid rain is obviously sulfuric acid. So there we are. So your oxides of nitrogen, so these are produced when nitrogen and oxygen are obviously heated in the air, as we mentioned before, in the car. And obviously these can form nitric acid, which also contributes to acid rain too. So there's a lot of different factors here, and you can see obviously what extent the burning of fossil fuels, particularly fuels that contain nitrogen. Obviously, nitrogen is found in the air anyway. When you burn anything, you obviously, by kind of proxy, you obviously react to the nitrogen with the oxygen as well. Okay, so it's a bit doom and gloom. So how do we actually kind of reduce the levels of sulfur dioxide and nitrous oxides as well? So the key thing is trying to neutralize these acidic gases. And actually there is an obligation on companies within the UK. There certainly is. Obviously globally other countries might have their own rules and their own laws, but generally there's a consensus that there needs to be something done to try and reduce the reliance on fossil fuels for manufacturing and energy. So removing in the UK, companies are obliged to try and reduce pollution levels, and they're penalised for polluting the atmosphere. So or polluting the atmosphere too much, should we say. So removing sulfur dioxide from flue gases, they use a process in industry called wet scrubbing, and it's a method where an alkali is basically used to neutralize the sulfur dioxide that's produced in flue gases. And you can see obviously a picture there showing a chimney that's obviously producing this. So wet scrubbing obviously involves dissolving calcium carbonate or an oxide, so this is from your group 2 topic, in water, and it's spray this on the acidic sulfur dioxide gases that basically go up through the flue. And obviously when it's sprayed on that, it obviously forms a salt, and then the salt can be collected and maybe is used potentially. A lot of industries could use some of these pollutants, but as long as it stops from going to the atmosphere, then that's going to be obviously a key point there. Obviously, generally there is a movement, as I said before, to move to much more renewable sources of energy. There's a big drive at the moment to try and move more towards that and become less reliant on fossil fuels, but also to try and make sure that there's that it's sustainable. That's the key thing, and people can obviously live and use these things. So that's it. It's a nice little topic with nitrogen and sulfur. Like I say, there's a full range of A-level videos for CIE on Allery Chemistry YouTube channel. Please hit the subscribe button and show your support. That'd be brilliant. Like I say, these slides are available to purchase as a bundle with other topics as well from my TED shop. If you click on the link in the description box below, you'll be able to get a hold of them there. Great value for money, and allows you to kind of revise and help you to boost your grade, hopefully. Right, that's it. Bye-bye.